We have recently seen the chain rule. To better understand how to apply the rule in a given situation to differentiate the composite of some functions, let us go back to the actual rule itself. Say you have y, which is a function, and it's the composite of these two functions f and g. Y equals f of g of x, which just simply means that to the input x, first you apply the function g, and then on that you apply f, and that is what your y is, the final output. So then if the function is differentiable, then by the chain rule, the derivative of y with respect to x is f prime of g of x, the derivative of f at g of x times the derivative of g at x. It is a little difficult to remember this. Initially it feels like a somewhat complicated thing, that you find it a little difficult to remember. With practice it happens, but what will you do? Say you want to better remember it. Is there a way of remembering it easily? Yes. The outside inside rule. The rule of course is going to remain the same. It's the chain rule, so this is how it's going to look. But let us reinterpret it. The outside inside rule, or rather interpretation, tells us to first differentiate the outside function f, keeping what is inside intact without changing it, and then we differentiate the inside function where the outside function no longer has anything to do. It is like entering a house. First you enter through the main door, and then you get to a room, the first room that you enter, and then there are some other inner rooms. So when you make your entry, the inner rooms are not affected, but then you enter one of them also there. So that's how you can remember this application of chain rule, and it works when more than two functions are also involved. You do it gradually. If there are, say there is a sequence of rooms, then you have to first enter the outermost room, and then after that you go to the inner room, then the next inner room. So like that it goes in a sequence. Let us see this in this example. Say you have this function sine of x square plus x. So here your x square plus x is the function g of x, which is a function of x, but on top of that you have sine also. So your sine is that outer function f, the first room that you are going to enter, and here entering corresponds to differentiating. So that means first of all you will differentiate sine. So that gives you cos, you already know that. So without thinking of what's going to happen to the inside, you just write cos. The inside remains the same. The inner rooms are unaffected by your first entry. And then you enter one of the inner rooms also. In this case, say there is only one inner room which you have to enter, and that means next differentiating the inner room. Well, it does not really make sense differentiating the inner room, but I mean the analogy. Differentiating the inner function is corresponding to entering an inner room. So then the derivative of this with respect to x is 2x, and here again, I mean at any stage all the available laws for differentiating a function, they apply. For example, to differentiate this, you will differentiate this plus, then you will differentiate this. All those things are there, and then you apply the power rule. So that way you get 2x, and for this one you are going to get 1. So that's the structure of application of the chain rule. Let us see another example in which it's going to be a little more complicated. Say this one, example 5, where we have to find the derivative of this function g of t, which is this composite function tan of 5 minus sine 2t. So you see that it's not exactly just two rooms. First you have the tan room, then inside you have this room, 5 minus sine 2t. But actually within this room itself there is another small room, sine 2t. Sine 2t means in this sine part of the room there is a little other room 2t. So there is another composition happening there itself. So let's see how we can apply the chain rule successfully with this outside inside interpretation and differentiate this. So we straight away write the derivative of g of t, that is g prime of t, which is d dt of this. So that means first of all we have to enter the tan room, and when we differentiate tan we get secant square. Secant square of this. The inner rooms remain unaffected on my first entry, and then I am preparing to enter the inner rooms. Remain unaffected here only, okay, but then that preparation should also be there along with that. Okay, next I am going to enter the inner rooms. So then I enter the inner rooms. This part of course remains the same, but however it has already been affected, that effect remains. Secant square 5 minus sine 2t. Now what happens? So I have entered the inner room. I have affected 5 and now it has become 0. Minus, now I am going to affect sine 2t, this sine part of the room, which itself has another inner room 2t. To emphasize that 2t is again another level that I have to enter, I am using another set of brackets, which normally we do not use. I mean, it's understood that we are not talking about the product of sine 2 and t. No, whenever you see sine 2t, it just simply means that we are talking about the sine value of 2t. Okay. So then this part of course remains the same, 0 minus. So what happens when I enter this sine part of the room? It gets turned into cos, but its inner part 2t remains unaffected even at this stage. But then now I am going to affect 2t, and when I do affect 2t I get 2. So now finally this is how this is where we are standing. Secant square 5 minus sine 2t times 0, if you want you can keep writing, but anyway it's going to vanish, minus cos 2t times 2. So let me write the final step. So the final answer is this, minus 2 times cosine of 2t times secant square of 5 minus sine 2t. So you see that if you keep this analogy in mind between differentiating a composite function using the chain rule and entering a house where there are rooms within rooms within rooms, then you can quite easily do the differentiation and get the answer, even if the given function is very complicated. So what I suggest is that you do a lot of practice with many examples, because differentiation is something you will need to do very often, especially if you are in science or some engineering branch. Okay, differentiation is the first thing that comes that you need to do. You should be fluent in differentiation, but you are going to need integration also. We will see those things later. So there are other things in this, other things means there are more examples in this section that we will see in the next video. And then finally there is a physical application also in seeing how ice melts when it is left outside, how a chunk of ice melts. So there is an application that we will study. So see you next week with more examples and possibly that application. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.